All right, so let's see if this goes a little better. Now we're going to talk about orbital diagrams. So orbitals can hold two electrons, and there are different numbers of orbitals in each sublevel. So sublevel F has one orbital, hence it can hold two electrons. Orbital P, you know now, can hold six electrons. So how many orbitals do you suspect it to have? Three orbitals needed to hold six electrons. The D sublevel, you know from the periodic table, there's 10 elements across, so it holds 10 electrons. So the number of orbitals that must be present then is 5, half of 10. And the F orbital from the periodic table, you can count across 14 electrons, 14 elements in the F section of the periodic table, and hence that needs 7 orbitals. So let me just quickly, since this isn't being done exactly as it should, there. So here is the S area, all of these in helium. So there are two elements here. That's why there's two electrons. This is the P area here. There are 6 elements across. That's why it can hold 6 electrons. Here's the D area that can hold 10 electrons because there's 10 elements. And here's the F area that can hold 14 elements and 14 electrons. All right, getting back to where we were. We were here. So that's where all that came from, how you know the number of electrons. And these are the number of orbitals. What does that mean? Well, that just means that we draw these little lines or sometimes boxes, if you prefer, to designate where these electrons are even more specifically. So we're focusing in even more from the 1s2 to s1 address to even more specifically what's going on. And there's two things you might notice if you take a look at this. The two things you might notice is, first of all, that the electrons don't ever go into one of these orbitals in the same direction. It's either one up and one down, right? Or just one up by itself. And the other thing you might notice is that rather than coupling up here, they go in their own space until there's no more space to go into, and then they start doubling up. So let's get into that a little bit more. So the first rule is called Hund's rule, the rule about how they don't double up. And if a sublevel has more than one orbital, so here the P sublevel, right? We have 3 orbitals in the P. And if you have more than one orbital available to a sublevel, the electrons don't want to double up. They will occupy the empty ones first. So it's sort of like if you're getting on a bus to Schenectady and there's some people sitting on that bus, you don't just, when the whole bus is empty, you don't go sit next to that person. No, you go to your own space, right? And that's sort of the general feeling on a bus, as you go to your own space. And when all the spaces are full, that's when you start doubling up. That's when you start buddying up with people, ask them if they can please move their stuff. They say no. All that happens. So that's Hund's rule. Hund's rule says that if a sublevel has more than one area, well, then maybe I can go forward. So, nope, I can't. Basically, if a sublevel has more than one orbital available, the electrons, I'm going to go back. I'm doing it. Hold on a second. There we go. So here, the second electron, carbon has 2 electrons in the P sublevel, right? 2p2. So rather than doubling up here, it doesn't do that. That does not happen. What happens is the next electron goes over here. So that's why that's like kids on a bus or whatever. All right, that's Hund's rule. Now, the other rule is the Pauli exclusion principle. When paired, electrons have opposite spins. So that means if you're in the same orbital, if one is going up, the other's going down. That was the other thing we noticed when looking at that. And there's a great video of this guy who does some thing with his arms. And basically, his 2 arms, if he were the orbital and his arms were the electrons, they would be spinning in different directions. And since I'm doing this anyway, let's do that. Let's check that guy out while we can. So here's that guy doing this thing. It's called Poifu. And, you know, people love it. Here we go. So this guy, you got to go way over here. So watch. He's trying to show you. All right. All right. So he's an orbital. He's an orbital and his arms are electrons. And in order for everything to be in harmony, everything has to sort of do backwards. That's DJ, by the way. I love that one. So look how there's harmony now because they're spinning in opposite directions. And that, my friends, is poi fu. And that is also what happens with electrons and orbitals. So thanks to that guy for doing that. All right, back to my thing. Here we are. All right. So orbital filling diagrams, Pauli exclusion principle basically says that electrons have to spin in opposite directions. So here's another way to look at it. If you consider the S orbital, the S subshell, as a two-seat car, right? There's one row, two seats. The first electron goes up, the second electron goes upside down. All right. The P subshell is like a three-row car. Whether or not you use all the rows, you still have three rows in the car, right? You may not use all those rows. You may not use all those rows. Sorry for this, right? Here's the three-row car. You may not use them all with all the electrons, but they're still there. It doesn't mean they're not there. So, should have made that one shorter. All right, here we go. So, the first subshell S, one S subshell, you always have one up, one down. For the P, you're going to go up, and then the next guy's going to go in the second row, and the next electron's going to go in the third row, and that's when you start doubling up as you go upside down in that, like that. The D subshell has 5 rows. So again, if you are drawing this, you have to show all 5 rows, even if you don't use them. So the first electron to go into a D that's D1. D2 will spin upward, D3 will spin upward, D4, D5 will all spin upward. D6 is where, and we'll talk about when this doesn't always true, we'll start going upside down and start buddying up. All right. So the S or a subshell, sublevel, whatever we call those things, is like a two-seat car. The P sublevel is like a three-row car, and the D sublevel is like a five-row car or vehicle. All right. So look here. So here's the D. As you can see, there is 5 rows to this D. Each one can hold 2 electrons, but you have to draw them all even if you're not using them. So scantium, which is 4s2, 3d1, the 4s is up and down, and then the D, the first one, is going up, and the other 4 seats, 4 rows, you still show the rows even if they're not being used, if that makes sense. The titanium 4s2, 4d2, 3d2, you show all 5 rows, and you only go through the first 2. All right, but you still show that there's rows there. Now you can see what's lovely about this picture. I said it, lovely, is it shows you, here's what I keep telling you, there's an energy benefit to having everything going in the same direction, and that's why they go in the same direction. And I compared it to if I had a hula hoop going around on my waist and I threw a second hula hoop on, it's nice to have it going in the same direction as the first, and a third one. So the same is true with these electrons. There's an energy benefit to having everything move in the same direction. And you may recall we said electrons do whatever is energetically favorable. They don't have ideas, they just do what they need to do. So here with chromium, you see it actually takes the one from the S orbital that was going in the opposite direction and kicks it over here. So now you have 6 going in the same direction. So it's 4s1, 3d5, but everybody's spinning in the same direction because there's an energy benefit to that. And then the next one to go in now starts going upside down and upside down. So this just shows you why they all go in the same direction. There's an energy benefit to having things go in the same direction. Will I ever ask you to predict this? Not in this class, but if you're taking a higher level class, you will have to be able to predict when things would break up like that and start spinning in the same direction. All right, so let's do one. So carbon has atomic number 6. There's 6 electrons to give. The electron configuration, if we look at a periodic table, and of course I don't have one of those handy. Let's find one. Let's find one. Here we go. So here's the electron. So we're going to carbon. No, thanks, Mr. Roach. Let's go here. We're going to carbon. So we're going to go through 1s2, 2s2, and 2p12. So it's 1s2, 2s2, 2p2. All right. This was not well thought out, but here we go. So there's 6 of these bad boys. 6 of these, and it's 1s2, 1s2, s2, 2s2, s2, and then 2p2. All right. Sorry about that, kids. All right. So here, the orbital filling. So how many orbitals are in the 1s? How many rows in the car? There's 1 row. It's 1s. And so you show the first electron going up, and you show the second electron going down. That wasn't pretty, but it's done. Now the 2s, how many orbitals does that have? How many can the s hold? S can hold 2. Each orbital can hold 2. So the 2s is just one orbital, 2s. And you're going to show an electron going up for one of those electrons and an electron going down for the other. Woo, thank you, Mr. Roach. Then 2p2. So now the 2p is a 3-orbital vehicle, right? It's a 3-row vehicle. So you have to show all 3 rows, even if you're not using them. And in this case, we're not going to use them. We only need 2 electrons in here. So our choices are, we're going to put 1 electron up because that's what we always start with. We can either put a second electron here down, or we can do like kids on the bus and go over 1. And there's an energy benefit to having things spin in the same direction. So that's why they go to their own space, make sure they're spinning in the same direction. So that would be for carbon, 1s2, 2s2, 2p2. All right, phosphorus is 15. I'll have you just look at your own thing. So electron configuration is 1s2. All right, and we're going to go all the way up to 15, 2s2, 2p. Someday I'm going to buy a pen, so this is a lot easier. 6. Look at that. Then it's 3s2. All right, that's a total of 12 right now. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. So I need to do 3 more. So it's 3p, 3p, 3. All right, so what that would look like then is the 1s is 1 orbital because it holds 2 electrons. And there's going to be an up and a down, up and a down. And then the 2s is going to be also 1 orbital. I don't know if this helps much. And it's going to be an up and a down. Maybe I should start using my finger. That is, how about that for a 2? All right, maybe I'm going to start using my finger. All right, so the 2p is 3. 1, 2, 3. Oh no, so that's 2p. That's working all right. All right, and it's going to be up, up, up. It's 2p6, so then we're going to go down, down, down. Huh. Should use my finger earlier in this. All right, 3s. How many orbitals in 3s? That would be 1 orbital, and it's got 2 electrons in it, so it's going to be 1 up and 1 down in that 2-seater. And then 3p again has how many rows in the car? How many orbitals? It has 3 rows, three lines, 3 electrons. So we're going to go up on the first. We could go down, but there's not an energy benefit to that. There's an energy benefit to having everything go in the same direction. So we're going to go up, up, up. So like that. And that is the 3p. Oh my goodness, Mr. Roach found that his finger works better. So that's how you do an orbital filling diagram. Now, another thing to notice, argon, where's my thingy? There he is. All right, argon, 1s2, 2s2, 2p6, 3s2, 3p6. If we do titanium, which is after argon, did I actually do this? I didn't. All right, so if we go back to a periodic table, it'd be nice to have a periodic table, wouldn't it, kid? All right, so I'll figure this all out someday. Here's argon, here's titanium. So you see how titanium's in row 4, period 4, argon's in period 3. So titanium, it turns out, is everything argon is, because we do this in order, like we had talked about in the other video of jumping around. Now, where am I? Where am I? I'm here. Nope, I'm here. All right, so argon, 1s2, 2s2, 2p6, 3s2, 3p6. Titanium is everything argon is, plus a little bit more. So we actually can do shorthand and say, for noble gases use only, so we use the noble gas from the previous row, argon, and that replaces all the things that argon is. So this argon in parentheses, in brackets, means 1s2, 2s2, 2p6, 3s2, 3p6, all that argon is. And then you add, oops, ignore this. Then you add 4s2, 3d2. All right, high quality stuff. So zinc, which is number 30, you can say is everything argon is, right, which is 18, plus argon. I thought I was going to use your finger, Mr. Roach. That's true. Argon plus 4s2 then, and then 3d10. So that's argon is 18, 2 is 19 and 20, and then plus 10 is 30. So that's what it is. So that's another way to look at that. And then the way to look at that orbital filling, I'll accept this as orbital filling just because I will, because it's otherwise a lot of work. So 4s would be up and down, and then 3d, D has 5 orbitals in it because it holds 10 electrons, and it's a 5-row vehicle. You designate it as 3d, and then it would go up, up, up for the first 5, and then the second 5 would go down, 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 down. All right. Lead, I'm not going to do that because I don't think you're paying attention anymore anyway. So here it is. All the elements after neon have everything that neon has, the 1s2, 2s2, 2p6. So we just write in brackets for 1s2, 2s2, 2p6, and everything beyond that is written for each one. Do you see that? So aluminum is everything neon is plus 3s2, 3p1. Did I do that last one right? Yeah, I did. So argon, here it is argon. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So you would say potassium is everything argon is plus 4s1, which is 19, argon being 18. So all of these come on after, see here, argon means 1s2, 2s2, 2p6, 3s2, 3p6. So it's just shorthand, so you don't have to keep writing all those things. I'll accept that on any quiz or test. All right, I am done with this, kids. Hopefully that helps, and it's shorter videos. So that should all be good, right? Now it's